Yeah, maybe. Yeah. Okay. Today it is a pleasure to have Julius Julius from École Normale Supérieure, and he will have a talk titled Rosetta Stone for Wilson line defects. Please, Julius, go ahead.
Yes, thank you. First of all, thank you very much for the invitation, and I'm very happy to give this online talk. So let me share my screen just a second. Okay, so can you see my screen?
Yeah, yeah, it's fine.
Okay, fine. So yeah, thank you again. Thank you very much uh, for the uh, for the for the invitation, and I'm very happy to give this talk. So I'll be telling you about a recent paper, this one that we wrote along with Nika Sokolova, who is a postdoc in DAISY, and she's also in the audience here. So she's also in the audience here. So this paper we wrote towards the end of last year, and it's titled "A Rosetta Stone for Wilson line defects." Um, so the reason for the title is the following, because there is so the general kind of thing that we're trying to do is we're trying to look at these holographic defect setups and try to see if in these defect setups one can ask the question of whether there is a smooth map of degrees of freedom between smooth map between degrees of freedom on the weak coupling gauge theory side and the degrees of freedom on the strong coupling string theory side. And in particular, there's a particular Wilson line defect that you can define in an equals 4 super Yang-Mills theory, which benefits from integrability. And as a result of that, some of these questions can be asked a bit more sharply. And if it is for that reason why we thought of calling this theory as the Rosetta Stone for Wilson line defects, because maybe it will give us some information. Okay, I'm going to try to do this. It's still, you can still see my screen, right? Now I just continue to share. Yeah.
Yeah, yeah, we can see it.
Okay, perfect. Okay, so having said that, let me introduce the characters of this game. So we will be working with n equals 4 super Yang-Mills theory. So let me give a brief description of what this theory is. So n equals 4 super Yang-Mills theory, it's an interacting four-dimensional superconformal gauge theory. And in particular, it has two parameters. So it has your usual Yang-Mills coupling GYM, and it also has the number of colors or the rank of the gauge group N. So we'll be focusing on SUN super Yang-Mills theory. And we have two parameters, G Yang-Mills and the number of colors N. And in particular, we will focus on what's called the planar limit of the theory. So in the planar limit, what we do is we take the Yang-Mills coupling GYM to 0. We take the number of colors N to infinity, and we do so in such a way so that a particular combination lambda, which is d square Yang-Mills times N, called the 't Hooft coupling, is kept fixed. The reason we take this limit is manifold, but the first reason is already when you take this limit, what happens is that the only thing that you need to worry about are single trace states. So there is some factorization that happens in this 't Hooft limit, and as a result of that, the only important states that one needs to worry about in this theory are so-called single trace states. And these states are made in the following way. So you take a trace, it's a color trace over a product of L objects. And these L objects are just the fields of your n equals 4 super Yang-Mills Lagrangian, the scalar fermions and field strength, uh, and with any number of covariant derivatives acting on them. So you have a trace of L objects, and each of those objects can be any of the fields of n equals 4 Yang-Mills with any number of covariant derivatives acting on them. You make L of such things, and these are the kind of states that you want to study. These are called single trace states. In particular, because these are the states that we're studying, and in particular we would like to label them, and these states of course are labeled by the bosonic symmetries that we have in this theory. So n equals 4 super Yang-Mills theory, as I said, it's a 4-dimensional superconformal field theory. So the bosonic symmetries are the 4-dimensional conformal group SO4, 2. And then there's also an SO6R symmetry. So this you can think of as some flavor symmetry. So the global symmetries of this theory are SO4, so the global bosonic symmetries of this theory are SO4, 2 times SO6. And as a result of this, there are 6 unique labels that can be used to label a state, and they are given here. So there are the first 3 are delta, L1, and L2. So these are 3 quantum numbers which label representations of your conformal group. So the delta is your scaling dimension, and L1 and L2 are angular momenta. And then there are 3 other labels, Q1, P, and Q2, and these three label they are the Dynkin labels of your SO6 flavor or R symmetry. So in particular, if you know all 6 of these numbers, they should give you a unique label of the state. Now, out of these 6 numbers, 5 of the numbers are integers or half integers, the L1, L2, Q1, P, Q2. However, the 6th number, which is the dimension, in general, it could be a non-trivial function of the 't Hooft coupling. So unless there is some reason why the scaling dimension is protected, in principle, a state could have some anomalous dimension. So in principle, the dimension is some non-trivial function of the 't Hooft coupling. And this is this is the place where the planar limit comes to shine again, because essentially what happens is that in this planar limit, there is an underlying integrability structure of n equals 4 Yang-Mills that comes to the front. And using integrability, basically, it is possible to solve the spectral problem. So to obtain, in principle, and also to a large extent in practice, the scaling dimensions of almost any state in the theory with any choice of quantum numbers. And the most I guess efficient is a good word to use it. Most efficient and probably the most modern avatar of this method is called the quantum spectral curve, and it was introduced back in 2013 by these authors here. So this is about n equals 4 Yang-Mills. Now I want to put a defect inside this theory. And the defect that I put inside this theory is the following. So what I do is I insert a supersymmetric Wilson line in n equals 4 super Yang-Mills. And that's given in the first line over here. So basically, you just have you have trace path ordered exponential. You have the usual Wilson line, but what you do is, along with coupling to gluon, you also introduce an extra coupling to 1 out of the 6 scalars of n equals 4 super Yang-Mills series. So before I explain a bit further on this, let me just go to the previous slide and give you one piece of detail that I did not mention. So as I said, there is this SO6 flavor symmetry, and the scalars of n equals 4. So n equals 4 super Yang-Mills has 6 real scalars, and these 6 real scalars are charged under this SO6. They transform as vectors under this SO6 flavor symmetry. So what you do to build the Wilson line is you pick one of them, 1 out of the 6. I'm just denoting that as parallel, and you couple that to the Wilson line as well. And when you do that, you get a supersymmetric Wilson line n equals 4 super Yang-Mills. Okay, so that's this operator W. And the reason why we introduced this is because now we've introduced a one-dimensional defect inside the theory, and in particular, you can start computing interesting observables. So the observables that one can compute now are these ones, are these double bracketed expectation values, basically. So what you do is you have your Wilson line. So you start at the point minus infinity, and you draw a Wilson line until point T1. And then at T1, you make an insertion of an adjoint valued field. And then you make another line segment between T1 and T2. And then at T2, you make the insertion of another adjoint valued field. And then you introduce another line segment make another insertion, and go on until you have made n insertions. And then finally, you take the last, from the nth insertion to infinity, you introduce the last Wilson line segment. And finally, to make everything gauge invariant, you take a trace over the entire thing. So you can define something like this, an observable like this, where you make n insertions at n different points on the Wilson loop, on the Wilson line contour. And this expectation value basically satisfies all the axioms that you would satisfy in a one-dimensional defect conformal field theory that was shown by these two authors back in 2006. And in this way, you can consider insertions on this Wilson line to be a one-dimensional defect CFT inside n equals 4 super Yang-Mills. In particular, what are the symmetries of this one-dimensional defect? So the symmetries are the following. So let's start with the symmetries of n equals 4 super Yang-Mills. So we have the SO4, 2, which is the four-dimensional conformal group. The insertion of the line, it breaks the four-dimensional conformal symmetry into one-dimensional conformal symmetry SO1, 2 along the line times SO3 global rotations around the line, right? So SO4, 2 breaks into SO1, 2 times SO3. And as I said, I picked one out of the six possible scalars in the theory. So because I picked one of the six scalars, I'm breaking the SO6 R symmetry into SO5. And as a consequence of this, now states in this defect CFT, they are labeled now by just four labels. So again, we have the dimension, which corresponds to SO1, 2, the spin. So this is some transverse spin corresponding to SO3. And finally, Dynkin labels M and N corresponding to SO5. So now we specify 4 instead of 6 numbers to specify a state. Okay, so let's actually see what happens to the fields of n equals 4 super Yang-Mills when we introduce these defects, right? So already, let's see what happens for scalars. So as I already mentioned, the scalars in the theory, they transform as vectors under the SO6 global symmetry, SO6, sorry, R symmetry. And because I chose a particular one, now what happens is that this, the 6 scalars that I have, they rearrange themselves in the following way. So now we have 5 scalars, which transform in the fundamental of SO5. They are labeled by this index M. And then we have one scalar which transforms as a singlet that's labeled by phi parallel. Similarly, in n equals 4 super Yang-Mills, we have fermions which transform. So we have fermions, and again, even the fermions, they under the presence of the defect, the way they transform also changes. And in particular, you can think about it as the identification of the dotted and undotted indices that you have for the two SU2s that make up the SU4 in the theory without the defect. For the field strength, what happens is that because we have picked one direction, again, we have now the field strength breaks. So F mu nu now breaks into 3 components F T I. So you pick T. So I put the Wilson line along the T direction. So I have three components FTI, and then I also have Fij, which are the remaining components. So, and both of these are transforming. Both of these are now have SO. So I and J are going from 1 to 3 now. And then finally, the covariant derivative also breaks because we have now the covariant derivative breaks into derivatives along the line and derivatives orthogonal to the line. And in particular, it's important to note here that because the conformal group is only along the line, therefore you can only generate conformal descendants by acting with covariant derivatives along the line. And in fact, actually acting with covariant derivatives perpendicular to the line generates new conformal primaries, super conformal primaries, in fact, as we will see. So this is what we have at weak coupling. Let's also understand what happens at strong coupling. So at strong coupling by the holographic dictionary, at strong coupling by the holographic dictionary, a Wilson loop is dual to a string, an open string that ends on the contour of the Wilson loop at the boundary of ADS. And In particular, what that means is now if I have this particular setup, I have essentially insertions on the Wilson loop on the boundary correspond to fluctuations of an ADS2 worldsheet that is created by this open string. Okay, so that's essentially what that's essentially what the degrees of freedom are at strong coupling. We have some fluctuations on an ADS2 worldsheet living inside ADS5. In particular, what are these fluctuations? So there are 5 bosonic modes which correspond to S5 fluctuations, and they are labeled by these letters YM. Again, M goes from 1 to 5. These are massless bosonic modes. There are also 3 massive bosonic modes corresponding to fluctuations in the ADS3 directions, and these are labeled by Fi. Again, I goes from 1 to 3. And finally, there are 8 fermionic modes. Again, we are allowed to take derivatives along the defect. So these are your letters. So at weak coupling, we have a whole bunch of letters. So we have all of these. We have phi m, phi parallel. We have psi plus or minus, FTI, Fij, and 2 types of derivatives, del I and del T. And at strong coupling, we have massless bosonic fluctuations, massive bosonic fluctuation, fermionic fluctuation, and derivatives along the defect. So these are the 2 different alphabets that we have. And
excuse me, can I ask where this identification came from? The dictionary, holographic dictionary, that the Wilson line equals to string, etc.
This is I think an old result from I think from the early days of ADS CFT. I think maybe even the paper, like I think there's a paper of Maldacena where he shows this. I think there it comes from that.
I mean, what is the logic? Do they kind of compare the quantum numbers of these 2 objects or something like that?
Maybe I can make a comment. By the way, there is the remark that 3 massive bosonic modes correspond to ADS3 is not correct. It's modes corresponding to directions in ADS5, which are orthogonal to ADS2. This is not.
Sure. Yeah. So
this is not. No, to answer the question is yes, indeed, it's part of the kind of expected correspondence. So you have a boundary of ADS5 is 4-dimensional. So on 4-dimensional boundary, you think there is a gauge theory where it lives. In gauge theory, you have a line. So if you imagine you have a surface which ends on a line, it's just like in flat space, you may say Wilson Wilson loop expectation value is represented by some effective string theory, where you have open strings which end on this line. I mean, the ends of open strings are on a line. So if you have, for example, a closed loop at the boundary or rectangular loop, that would be like 2 quarks propagating and annihilating. And the open strings attached to quarks. So there is a minimal surface which is like a hat ending in the circle.
So this is the analogy with the D-brain construction where you have open strings.
It's indeed, you think of boundary being like a D-brain, you have open strings ending at the boundary. And then you have a circle, say you have a circle or a line on the boundary, you have open string attached to it. And the main postulate is expectation value of this Wilson loop should be represented by a partition function or path integral of open string and ADS, which ends at this circle. So this minimal surface is like ADS2. It's like topology essentially like a disk, but it's embedded in ADS5. So,
thank you.
But then this fluctuation story is on top of that. So you need to think about small fluctuations of a string near this minimal surface, what they correspond. But anyway, maybe that's better not to go too deep into it. Yeah.
Okay, thank you.
Thank you, Arkady, for the comment. Okay, so right, so these are the as I was saying, the two alphabets that we have, one on either side at weak and strong coupling. So now let's see what happens. Now there's the particular Wilson line that we're working with. It's also supersymmetric, and as a result of this, basically, it's not just a one-dimensional defect conformal field theory that you have. You actually have a one-dimensional defect super conformal field theory, and in particular, that means that all of the various kind of states that you can define by making various insertions on the Wilson line at weak coupling, for example. All of these various states, they organize themselves into super conformal multiplets. And in particular, what you can do is you can kind of, what has already been done is that you can study these super conformal multiplets and try to understand what form they are. So in particular, in this particular defect super conformal field theory, there are a number of type of multiplets that we have, and they are given in this table. So I would ask you to focus on the first row of this table. So these are what are called long super multiplets. So these are just super multiplets with SO3 so these super multiplets are associated with some super primary operator, and the super primary operator has SO3 charge L, dimension delta, and SO5 linking labels M, N. Then what happens? You start with your super primary state. You act on it with various Qs with your supercharges, and then you build other conformal primaries, which are super descendants. So they're super descendants of the super conformal primary, but they are conformal primaries themselves. And then you take all of these conformal primaries, and you can build usual conformal descendants of these primaries, and all of these states together form one super conformal multiplet. And all of the states in a super conformal multiplet will have the same anomalous dimension, and that's the anomalous dimension of the super conformal primary state. So in particular, we just need to study the super conformal primary state. And if you look at the first row here, it tells you that there's a type of multiplets called long super conformal multiplets. And for these long super conformal multiplets, there is some unitarity bound. Basically, the dimension has to be greater than some combination of the other charges of the superprimary operator. Now, there are other special cases where essentially either the unitarity bound gets saturated. So instead of the dimension being greater than the sum of the other quantum numbers, it's equal to, or some other special points where what happens is that you still get super conformal multiplets, but these multiplets are what are called semi-short or short multiplets. And these usually have protected anomalous dimension, and also they're called semi-short or short because some combination of Qs of supercharges acting on the primary state will create a null state, and therefore the multiplet itself becomes smaller. But anyway, the purpose of this slide is just to tell you that there is a super conformal multiplet structure also inside this defect CFT. Okay, so once we know all of this, let us try to actually enumerate states in this one-dimensional defect. So as I said, that at strong coupling, there are various degrees of freedom. So there are these fluctuations, massive and massless fluctuations, as well as fermionic modes. And all of these fluctuations can be captured inside a single super conformal multiplet of type B1. Okay. So essentially, states at strong coupling can be built by you take each of these three degrees of freedom as some letters, and you build words using these letters, and also with any number of derivatives along the line. and you can build states in the theory by building all possible words with various choices of letters, so that they correspond to the particular symmetry group that symmetry sector that you're focusing on. So that's what it is at strong coupling. There's just one superconformal multiplet that captures all of the degrees of freedom. At weak coupling, actually, the degrees of freedom, there are more degrees of freedom, and it's a bit more complicated. So there are actually infinitely many more super multiplets that are needed. So first of all, already we know that at weak coupling, there is this extra scalar phi parallel. And this extra scalar phi parallel is also a super primary of some A2 type super multiplet. So we need to include this at least this extra multiplet. I had also made a comment a few slides ago that because the covariant derivative breaks into derivatives along the line and orthogonal to the line, actually now derivatives orthogonal to the line again generate super conformal primaries. So indeed, for every symmetric combination of covariant derivatives orthogonal to the line, acting on this phi parallel and acting on this parallel scalar, we will get it will form at least a part of a super primary of a new super multiplet of type A1. So in particular, so since there is one multiplet associated with with one choice, with one rank of SO3 that you can, a rank representation of SO3 that you can build with these covariant derivatives, there are actually infinitely many more super multiplets that we have now in the game. Okay, so now I've told you what are the two alphabets at weak and strong coupling. I've also told you how these alphabets can have to be thought about from a super conformal field theory point of view, like how they organize themselves into various super conformal multiplets. So now let's actually see how we can count steps. So this is just going to be a very lightning review of how this thing is done. So essentially, there is something called platistic exponent, and what the platistic exponent does is the following. So if you know what are the possible letters, what are all the possible single letters that you have in your theory? What are all of the possible single letters that you have in your theory? The platistic exponent is essentially a machine that takes that in and gives you what are all of the possible multi-particle words that you can make. So the easiest example is this. Suppose I have just one letter corresponding to one bosonic degree of freedom. Then of course the number of all of the words that I can make are, well, I can do nothing. I can insert this letter once. I can insert it twice, thrice, etc. And this resums to, so if I want to make the partition function, I have to add all of these things. So I have 1 plus 5 plus 5 squared plus 5 cubed, etc. And this resums to 1 over 1 minus 5. And the platistic exponent essentially, it does the exact same thing. Of course, this is an overkill from the point of view of just enumerating a single bosonic letter, but the platistic exponent is useful when the single letters are more complicated. For example, if the single letters are associated with some global symmetries, etc., etc. Again, if you have a fermionic degree of freedom, then also you can modify the platistic exponent so that it makes sure that no fermionic letter can act more than once, because you should not act more than once. And again, there's an easy example, but then in general, this formula can be used. I also mentioned that in general, the power of platistics is useful when there are global symmetries. So essentially, when you have global symmetries, what you do is you dress your single letter along with the character of the representation that the field associated with that label transforms under, the character of the global symmetry representation that it transforms under. And the reason that you do this is because now you can just take everything, plug it into your platistic exponent, generate a huge partition function with all of these character variables involved. But then at the end of the day, you can then use character orthogonality to project yourself onto specific symmetry sectors that you're interested in. So that's why it's useful to use these characters to keep charge of global symmetries. So let me give you an illustration. So at strong coupling, we just need the single letter partition function. So we just need the single letter associated with this B1 multiplet. So there are three types of fluctuations. There's the scalar fluctuation. The scalar fluctuation doesn't have, so we can write down, okay, let me explain what this Z strong means. So forget for a moment this 1 over 1 minus q, and let's look at the three terms inside. So the first term is chi, is some character, and it's the character associated with this fluctuation ym that I was telling you about. So this is a bosonic fluctuation that transforms in the fundamental of SO5, and it has dimension 1. So that's what you can see here. So inside the first square bracket, we have 0 because it's bosonic. It doesn't have any spin in SO3. The superscript 01 corresponds to the fact that it transforms in the vector of SO5. And the subscript 1 corresponds to the fact that it has dimension 1. So that's for the scalar. The fermions all have spin half. So here it's 2 times the spin, basically. So that's why we have 1 in the square brackets. They transform under the fundamental of SP4, actually. So that's why they have 1, 0 there. And finally, they have dimension 3 halves. And finally, we have the bosonic massive fluctuations. They all have, they all have spin 1. So they have 2 in this square bracket. They are not charged under the R symmetry. That's why they have 0, 0. And finally, they have dimension 2. That's why the subscript is 2. And this entire thing is multiplied by 1 over 1 minus q, because 1 over 1 minus q is what you get when you take all of these conformal primaries and generate generate all possible conformal descendants from them. So that's what you have for strong coupling. At weak coupling, again, similarly, I told you that there are infinitely many multiplets, but then you can write a character associated with each multiplet, and then the form that you get is given in Z multiplets. Of course, there's a fundamental difference between weak and strong coupling, being that at strong coupling, you just have fluctuations you just have letters, basically, which are commuting with each other. So you don't have to worry about what order, about the ordering. But at weak coupling, I'm inserting matrices, right? I'm inserting adjoint valued fields inside the Wilson loop path ordered exponential. And as a result of this, we need to keep track of the order. So here we actually use so in order to keep track of this, we make use of a very interesting trick that Nika actually came up with, which is we say that let us actually, instead of so what we do is we just introduce, in addition to the single letter partition function of the weak coupling alphabet, we also introduce an extra letter associated with the Wilson line itself. And the reason we do this is because now what you can do is there are sophisticated methods which can compute placistic exponents in these theories where your letters don't commute with each other. In particular, it can count. There are methods to count single trace operators. So now by introducing this extra trick and this extra letter, what we can do is we can say, okay, fine, I will count now single trace operators, where I also allow the introduction of one extra letter associated with the Wilson line. And then what this counts for me basically are adjoint insertions, but keeping track of the order. So I can explain a bit more. I can explain this again later if there are more questions. But I'll go on just in order to stay with the time. So so once one goes through all of this procedure, and in particular, all of this was done by Pietro Ferrero Carlo Meneghelli back in 2023, one can actually enumerate the partition function of this theory at weak and strong coupling. In particular, the result displayed here is when you restrict to operators that transform under singlets of the entire global symmetry. So I just want operators which transform under singlets of the SO3 and singlets of the SO5. So the way you should understand this partition function is that so Q is just a fugacity associated with the dimension. So Q squared means that there is a state with dimension 2. Q to the power 5 means there's a state with dimension 5. And the coefficient in front of it tells you the number of states. So in particular, if you look at the weak coupling, it tells you there is one state at dimension 1, 2 states with dimension 2, 6 with dimension 3, 25 with dimension 4, etc. And then at strong coupling, again, there is 1 with dimension 2, 2 with 4, 4 with 6, 4 with 6, etc. Okay, so that's how these things should be interpreted. Okay, so now I've told you how one enumerate states both at weak and strong coupling. But the good part about this particular Wilson line defect is that it also inherits the integrable structure that we have in n equals 4 super Yang-Mills. And in particular, we can therefore use integrability methods of n equals 4 super Yang-Mills. We can use them in this context as well. So yeah, from that point of view, let me give you a quick crash course in ADS-CFT integrability. So this goes back to a classic paper of Minahan and Zarembo in 2002, which opened up this integrability direction in the context of ADS-CFT. Of course, there were works of Korchemsky, Lipatov, and others earlier in QCD context. But this was the first one in the ADS-CFT context, though the ideas are quite well, at least in the same, morally, they're in the same direction at least. So what Minahan and Zarembo showed that was the following. So suppose you want to consider just scalar operators so now let's remove the defect, let's remove everything, let's just go back to basic n equals 4 super Yang-Mills, and let's consider operators that I can make up of just 2 complex scalars. So out of 6 possible scalars, I take 2 scalars, x and z. So x is phi1 plus I phi2, and z is phi5 plus I phi6. I take a trace with L of these things inside, so some products of x's and z's of length L, and I want to compute anomalous dimensions of such states at one loop. So essentially, what this requires one to do is it requires one to compute a mixing matrix of 2-point functions of 2 to the L of size 2 to the L times 2 to the L. So you need to compute all possible operators with x's and with all possible numbers of x's and z's of length L, and compute all possible 2-point functions between these operators, compute a matrix of these 2-point functions, and then diagonalize it. And when you diagonalize that matrix, the eigenvectors will give you the eigenvectors of that matrix will give you the combinations of x's and z's, of traces of x's and z's that are the eigenoperators of the dilatation operator, and the eigenvalues will give you their one loop anomalous dimension. Now, even while describing it, it's quite clear that this is quite a hardcore thing to do. But that's where the magic of integrability comes in. So Minahan and Zarembo basically showed that this mixing matrix is essentially just can be mapped to the Hamiltonian of SU2 integrable spin chain. Okay, the usual Heisenberg XXX spin chain. You can just map the mixing matrix to that spin chain Hamiltonian, and that's it. So now, once you do that, basically it opens up all of these integrability techniques for you. You can just use Bethe ansatz, for example, and try to extract the anomalous dimension. So it actually makes the problem quite easy. So this, of course, what I described was just for a particular subsector of scalars at one loop in n equals 4 super Yang-Mills theory, but actually this integrability structure, it persists for all sectors in the theory at all loops as well, and even non-perturbatively. But just to illustrate, this is the easiest way to illustrate. So this is just the first instance of it. Now let's see what happens to this in presence of a defect. So in presence of a defect, basically what happens? So on the left side, we have a picture where I don't have a defect. So I have two single trace operators. They are these two circles that I have here with some number of fields inserted. Now, as you can see at tree level, the only type, because I'm also in the planar limit, the only thing I can do is I can connect each of the corresponding fields to each other. And then the one loop effects basically is this nearest neighbor effects, this nearest neighbor interactions that you have between two of these lines, connecting two elements of two of the traces. And of course, the important thing is that the important thing is that because we have a single trace operator, we have a closed spin chain and there is periodic boundary condition. So that means that if I start with the first element in the trace and I go to the last element of the trace, the last element can interact with the first element of the trace and still retain planarity because of the periodic boundary conditions or the closed structure of the trace, right? But that changes when we have a Wilson loop. So essentially, when we have a Wilson loop, the first element in the insertion, the first element of the insertion cannot talk to the last element of the insertion. It cannot talk because there is a Wilson line in between, right? But these sites, of course, sorry, I should have been using the word site, but these sites, of course, can talk to the Wilson loop itself. So in particular, suppose I have some scalar inserted at the top here. I can connect the two scalars. So on the right picture, I can connect the two scalars from one to the other. But then those scalars can, for example, exchange a gluon with this Wilson line, which I have denoted by this blue circle outside. So essentially, what you get is that in the usual n equals 4 case, you have some SU2 Heisenberg spin chain with closed boundary conditions and now closed periodic boundary conditions, and then now we have essentially the same spin chain but with open boundary conditions. Okay, and the reason that is useful is because now one can use what's called the method of images. So what you can do is you can just think of this open spin chain as just a closed spin chain but with double length, and then you can use this method of images and still attack it from as if you were looking at a closed spin chain. So that's what this buys you. So let me give you an illustration. So right. So now suppose I insert the defect again, and now I'm back in the scalar sector of the defect. So I only allow insertions of scalars on the defect, and these scalars can be either orthogonal to I can either be the scalar that couples to the Wilson line or orthogonal to it. It doesn't matter. I can insert any of the scalars. So now what happens to the spin chain Hamiltonian? Basically, you get the same spin chain Hamiltonian as Minahan and Zarembo, but then you get these two boundary interactions. You have now these two boundary interactions. So when the last or the first site is a parallel insertion, this can also talk to the line, and so you need to take that into account. But apart from that, you can do the same Bethe ansatz or whatever your favorite method is to diagonalize this Hamiltonian. I mean, for small Hamiltonians, you can also directly diagonalize them, and then you will get some eigenvectors and eigenfunctions. So that's just an illustration. And in particular, as I said, one can in particular use the method of images. So basically, if I just have insertions on the Wilson line, the full one loop spin chain Hamiltonian. So this is the spin chain Hamiltonian capturing all insertions on the Wilson line at one loop. This is not available yet. But what one can do is, using the method of images, actually just map the defect to an operator with double the length in n equals 4 super Yang-Mills. And then you can just use the n equals 4 super Yang-Mills result and double it and at least and use it basically. So I'm skimming over some of the details here, but that's basically the point. You can use the method of images to just take mileage from already stuff that you know in n equals 4 super Yang-Mills. And in particular, what you can do is in general for any state in this defect CFT. So with dimension delta naught, spin L, and SFI Dinkin labels M and N, you can actually just map it to a multiplet in n equals 4 super Yang-Mills, and then you can just study that multiplet at least at one loop in order to learn something. Of course, once you study it at one loop, then you have to go back and do all of this quantum spectral curve story in order to solve the full spectral problem of the defect itself. And again, that's the topic of a totally different talk. But I will show you the result of that computation. And that.
Can I ask a question?
Yes.
I'm missing something. So when you consider, say, closed string sector or single trace operators, so the Hamiltonian computes anomalous dimension. Anomalous dimension is like 2-point function of these single trace operators, right? So trace fields are multiplied. In the case of Wilson loop, you have each field is between some insertion of the piece of Wilson loop. So your correlate is built out of these fields with insertion of Wilson. So my question is, so when you talk about anomalous dimensions of this one-dimensional theory, that's the operators which you're looking at. The operators inserted on the line.
Yes.
With kind of Wilson loop between them. So suppose you have several fields, not just single field inserted at a point in Wilson loop, but you can have several fields inserted. How you will see the difference?
Okay, good. I want to draw. Let me try to see if it is possible to. I'm unable to access my mouse. Okay, good. Good. Maybe annotate. Okay. Now, for some reason, sharing the screen is not letting me. Okay, one second. I'll stop sharing and then I'm going to reshare. Just a second. I got your question. So there is a slight. There's a slight. So maybe I can draw in a whiteboard. I think that could be easier.
If you need me to do anything, I'm there. Thanks.
No, I just. Is there a way to get this? Is there a way to get just this whiteboard where you can annotate? New. Okay, maybe.
Yes. I mean, it's there by default. Yeah, okay, good.
Can you see it? It's okay. It's still loading.
Well, I do. I've even left a dot.
Okay, perfect. Okay, so right. Okay, so good. I drew a line. Right. So let's consider it like this, right? So this is the Wilson line. I have some insertions here. So basically, I build insertions in the following way. I insert a bunch of fields at the same point, and then I have another line segment, and then I insert another bunch of fields here. So the 2-point function I'm talking about is between this set here and this set here. So that's what I mean. So it's you have a bunch.
Okay, but in principle, you can just have the correlation. You can consider correlation functions with just one field.
Yes. But that would just be like, so I can do so you're saying, okay, this is the line. Sorry. Okay, this is the line. I do one field here, and then I do one more, of course. So at a 2-point function. So from the spectrum point of view, the QSC will just give you this 2-point function. This one, like this, for example, this is one of the one of the states that you will see with QSC. But of course, if you put more stuff here, right? If you put another one here, this already becomes a higher point function in the defect CFT. So this the quantum spectral curve. You will not get this from the spectrum. You will need something.
Okay.
Yeah. Okay. Now I will go back to. By the way, how much more time do I have?
If it's about time, I would say, I don't know, 15 minutes.
Okay, good. Thank you.
Thank you.
Okay. And just 1 second. I managed to open this thing in such a way that I'm not able to see my own cursor. So just a sec, I'll just try to reopen it. Mm. Okay, I'm here, so let me try to share. Okay. Okay, so it's gone again. Okay, sorry. Again, sorry about this. It's the first time I'm using Keynote. I usually use PDF. I thought this will be easier, but it's more complicated. Just 1 second. It's reopening. So you should be able to see my screen now, right?
Yes.
Yep.
Okay, perfect. Okay. Right. So I will skip the details because this QSC construction, as I said, it's topic of an entire other talk. But at the end of the day, what you can do is you can actually compute. You can compute this the dimensions of these insertions. So in particular, if you restrict to the singlet sector, so states which are not charged, then their dimensions can be computed from weak to strong coupling. So in this picture, that's what we can see. We have on the left side we have 0, and on the right side we have infinity. So we're going from weak Tooft coupling to strong Tooft coupling, and we're computing the dimensions of various states. In particular, maybe this also related to Arkadi's question. So the state with dimension 1 here, this is just a state with where I made a single insertion of phi parallel of this phi parallel on the Wilson line, right? I made one insertion of phi parallel, and then after some time I made another insertion of phi parallel, and this 2-point function is what I'm computing for the first line here. So, okay, so this, so from this picture, we already see something. We see that, okay, on the left side, basically, on the left side is the partition function essentially at 0 coupling. So this is, if you remember from a few slides ago, when I showed you, so that the left side basically is the first equation here. It has one state with dimension 1, 2 with dimension 2, 6 with 3, 25 with 4, etc. And then on the right side is the equation at the bottom here. And we can see that indeed the states are mapping. So the partition functions and weak and strong coupling, you can map from you can literally take the states at weak coupling and then map them to strong coupling. Of course, there are certain comments that I have to make here. The first thing is that, okay, we have one state at dimension 2, 2 at 4, 3 at 6, 6 at 3, but then at dimension 4, there should be 25. We only actually managed to find 19. So there are some missing states here at dimension 4. There are lots of missing states at dimension 5, 6 onwards, but then this is more of a, it's not that there's no contradiction. Basically, it's just states that are a bit more complicated to find using this quantum spectral curve method. But conceptually, there is nothing stopping us. So, but still, from qualitative point of view, at least we can see that there are two spectra and we map between them. So now, now let's try to understand a bit more what are these states, and let's try to see if we can actually do what I said at the start of the talk, which is, can we try to find some smooth map between degrees of freedom or between these alphabets at weak and strong coupling or zero and infinite coupling. So, okay, so we introduce the following notation. So we define a single particle state to be a state that is composed of a single element of one of the supermultiplets. And in particular, the relevant supermultiplets from our point of view are these ones. So they are the ones that contribute to the single letter partition function, the thing that you put inside the platistic exponent to generate the full partition function. So there is one multiplet whose superprimary is uncharged under the SO3. It has it has dimension 1 and its vector of SO5. This is this phi m. Then there's another one which is again not charged under the SO3. It's not even charged under SO5, and it has dimension 1 at zero coupling as well. This is phi parallel, right? And then there are other multiplets, for example. So as I said, the associated field content of these superprimaries are easy to deduce. For the first three that I've written here, they're very easy to deduce. So it's just phi m for the first one, phi parallel for the second one, and a particular combination of this covariant derivative, this orthogonal covariant derivative acting on phi parallel, and the field strength for the third one. Okay, so for those three, it's already known. Actually, I should have put a citation here, I think, to Drucker, Cook, and Deckel. I think they understood this, at least at weak coupling. But then for higher multiplets, the superprimary, it is still unique, but it is a linear combination of basically three different type of insertions that you can have. So the three different type of insertions are basically covariant derivative, orthogonal covariant derivative del I times phi parallel, the component of the field strength along the line, essentially, so FTI, and finally some epsilon acting on the other components of the field strength. So you have to make, so the superprimary will be some linear combination of these three, and the other two linear combinations of these three will be some super descendants. But in general, superprimary of a multiplet with dimension 2j, with dimension j plus 1 spin 2j, spin j dimension j plus 1 and no R charge is just this. It's some symmetric combination of some number of covariant derivatives acting on some linear combination of these f's. And the exact linear combination has to be fixed by explicit computation. So we refer to all of these states as single particle states because all of these states are generated from one element of a supermultiplet. Okay. We also introduced the concept of something called two-particle worlds. So what one can do is I explained earlier how one can compute these partition functions made up of different number of partition functions given the letters that you have. In particular, what one can do is not just keep track of global symmetries, but one can also keep track of number of particles. So you can associate special fugacities. You can associate a fugacity with each supermultiplet. And then when you compute your partition function, you can see how many words have contribution from how many different supermultiplets, etc., etc. And this also, in principle, can give you some new information. So in particular, I want to draw your attention towards the last line in this slide here. So what we did was we restricted the partition function to those words that are composed of two particles. So that means those words that are composed of at most, well, not at most, that are composed of exactly two elements of supermultiplets. And then we associate, with each supermultiplet, we associate this fugacity L. So what this tells us is that at dimension 2, there are two words that we can make two words that we can make with exactly two particles. And these two words are the following. There is one word which has two elements of one particular supermultiplet associated with the fugacity L1. And the other word has two elements of, again, one supermultiplet associated with the fugacity L2. The same holds for dimension 3. But of course, at dimension 3, essentially what this tells us is that I have the same combination of letters that I had earlier, but now I increase the dimension by acting with covariant derivatives along the line. Because covariant derivatives along the line, they are for free. So you can act with them as many as you want, and you will not increase the particle number. At dimension 4, there is a new multiplet that enters the game, which is associated with this fugacity L3, and it contributes a two-particle word. The same states for dimension 5. At dimension 6, again, there will be a new element. So yeah, as I said, so the fugacity, I should have put this line maybe in the previous slide, but the fugacity Lj plus 2 corresponds to a supermultiplet with primary 2j, j plus 1, 0, 0, right? So if I have, so basically it tells me here that there are two elements of that supermultiplet corresponding to this, that are generating this word. Now you can further refine this counting by introducing fugacities that also keep track of number of covariant derivatives along the line that you're acting. And then from that, you can easily see essentially that if you look at these two particle words, the possible two particle words that you have are given by this equation in the middle of this slide. So the two particle words are the following. So initially we have a state with phi m squared. So that contracts the m index, the SO5 index. So now this is a singlet. And I can make a conformal primary acting with 2k minus 2 covariant derivatives on this. So not a conformal primary, sorry. I can act with 2k minus 2 derivatives along the line. And then the dimension of this word will be 2 plus 2k minus 2. Yeah, indeed. And so the dimension of this word will be 2k. Similarly, I can generate that with phi parallel as well. I can generate the same dimension word also by taking the third element, squaring it, but now acting with less number of derivatives. And then I can take higher states, again, square them to contract all of indices, and then compensate for the number of and act with appropriate number of derivatives to make a word with particular amount of dimensionality. Okay. And essentially, what this tells us, if we go back to the equation here, the last equation on this slide, it tells us that essentially that there is a new tower of these words that gets generated at every even dimension. So at dimension 2, I had two words basically, phi m square and phi parallel square. At dimension 3, I still have phi m square and phi parallel square, but then I'm also allowed to act with one derivative. At dimension 4, I again have phi m square, phi parallel square. I can act with two derivatives, but now I also have this f hat square. And then at dimension 5, I have phi m square, phi parallel square, f hat square with so phi m square, phi parallel square with 4 derivatives, f hat square with 1, etc., with 3 actually. And then no, it's actually four derivatives and f hat square with 1, etc., etc. So I can keep generating a tower of states in this way, a tower of words in this way. Okay, good. So these are the type of words that we have. And now we can try to see if we can actually make some kind of a map between degrees of freedom. Okay. So let's try to do it first for single particle states. So as I said, the single particle states are just phi parallel, phi m, and all of these f stars. Now, the fact that phi parallel goes to ym square, this was already, this was some evidence for this was already given in a paper of Arcadi along with Simone Giombi and Rado Roiban back in 2017. And then by explicit computation of the dimension of that state with Nikolai Gromov and David Grabner, we also showed that indeed that's what happens. Both phi m and ym are superprimaries of a B1 multiplet and they have protected dimensions, so it's natural to expect that they will go from one to the other. So basically, what we kind of proposed with Nika was that we take for all of the higher single particle states, which are labeled by f star with any number of indices, we say that this state will map the lowest superprimary in the corresponding global charge sector, which happens to have double the dimension of the state at weak coupling. So this is what we proposed, and then we went back. We did some quantum spectral curve numerics, and then we actually found this to hold. So here, the first state is just this phi parallel state, which was already known since 2020, which goes to a state with dimension 2. And then the state with dimension 2 has spin 1, the state with dimension 3 has spin 2, state with dimension 4 has spin 3, and they are all going to double their dimension. So this is consistent with the map that we proposed for single particle states. Now let's see what happens for two particles. So for two particles, it's a bit more complicated. So of course, we try to take as much as we can from the single particle picture. So what do? We would like basically to map the ym square, the entire tower of derivatives of this ym square state. We would like to map it to a tower of derivatives acting on the entire tower of derivative of the phi m square state. We want to map it to the ym square tower. But the problem is that the ym square state with no derivatives acting on it, it's already mapped to phi parallel, as we know already from 2017. So we will somehow have to skip that state. And essentially what this does is it pushes the entire tower up by one step. So now what we say is that the entire tower of derivatives that are generated by phi m square, they map to the shifted tower of derivative generated by ym square. In particular, again, if you analyze the partition function, you will also see that in the strong coupling alphabet, the towers are generated with 2n number of derivatives rather than n number of derivatives. So you always have even number of derivatives. And that also then implies that the covariant derivatives on the weak and strong coupling picture map in the following way. So you have one derivative in the weak coupling picture that has to map to two derivatives in the strong coupling picture. Now we also have the result for phi parallel going to ym square, as we know already from before. We want to extend this map just by saying that, okay, any two particle state tower the two particle tower, not state, the two particle word tower, phi parallel square n, that maps to this 4 particle tower ym to the power 4, again now with 2n number of derivatives, because we already said that the covariant derivatives double. And lastly, we demand a similar sort of behavior similar sort of behavior for these higher states as well. Now, this very ugly notation that we have, f tilde star j, this is a unique word which has double the fugacity content as f star, So little f star is the strong coupling image of this double script f star. And f tilde star j is a unique word that has the double fugacity content of that word. But that does not mean that it is the square of that word, because in principle there are multiple ways that one can. There are more than one. There are multiple linear combinations that could lead to it, so it doesn't necessarily have to be the square of that word, which is why we had to introduce this extra notation. Anyway, so at the end of the day, this is the map that we propose. We say that the entire tower of phi m square goes to a tower of ym square, but shifted up by 1. We say that the tower of phi parallel square just goes to a 4-particle tower, not shifted at all, and then there are maps between other towers as well. Now, of course, this is a map. We have to say some caveats here. So the first thing is that the true superprimary states at some dimension can in principle contain contributions from any number of from words made up of any number of particles, right? So strictly speaking, this map is only a map from a set of words at 0 coupling to a set of words at infinite coupling. In strictly speaking, it doesn't imply anything for the states themselves. But if the superprimary can be constructed just out of 2-particle words, that means if 2-particle words are 2-particle states, then our map indeed predicts that the dimensions of these 2-particle singlet superprimary states will double as they go from 0 to infinite coupling. So only if that's the case, then this map makes this prediction. But okay, so then let's actually see what we get. So it turns out that, again, if we use this method of images mapped back to n equals 4 super Yang-Mills, we find that there is a subsect of states which are accessible by the quantum spectrum curve, whose number grows precisely like these 2-particle words. We also see that all of these states are generated they can be mapped to a particular type of, like a single multiplet inside. So for every choice of the bare dimension, you have a single multiplet in n equals 4 Yang-Mills, which gives you these states. And lastly, for the highest particle subsector, the one-loop Hamiltonian is known, and it is known that the states that are captured, that these states are not those highest particle states. So combination of these 3 evidences basically allows us to conclude that at least at one loop, the 2-particle words do form 2-particle states. But at one loop, at one loop, we can still say that there is some notion of 2-particle state. So let's look at the explicit result. So here are those states, and indeed we see exactly what we predicted. We see that there are a bunch of states which have this slow growth as we get from the counting, and all of them go from dimension delta to 2 times delta from between weak and strong coupling. So this, in some sense, gives credence to the map that we have. Of course, there are certain caveats which I will present in this discussion, and I need just another minute, and I will conclude. So the first of all, we had something where the dimension is going from delta to 2 delta, but the generic expectation of a smooth map of degrees of freedom is that actually the states which have some dimension at weak coupling, they go to the square of that dimension at strong coupling. Here, I forgot to put a citation. So this is a recent work of Viktor Gorbenko, Jashin Baragabai, and Bendeguz Offerteller. So they make this generic expectation a bit more concrete. However, I would like to emphasize that this is not necessarily in contradiction with what we are saying, because they are considering generic theories which are non-integrable, and we are considering integrable theories, and integrable theories allows for level crossing. and therefore the target dimensions can be lower if you allow for level crossings. So that should be fine. It was very crucial that two particle words formed states at one loop to even be able to define a map. Of course, at higher loops, you expect there to be admixture from higher particle states. And also at strong coupling, you know that the eigenstates are made up with contributions of multi-particle states. So it is interesting, of course, that even though you wouldn't expect this map to persist, maybe you wouldn't expect this map to persist, it does. So that the map works, it really seems to suggest that there is still some notion of effective particle number that allows us to grade states. And that's why this map seems to be working. It could be a sign of some new hidden symmetry, or it might actually just be what characterizes the integrability of this model. So this is something to think about. We don't really have that much idea of what this could be, but I think this is an interesting direction to think about. And yeah, and this is my last slide. So I can just basically leave it here. There are various things to do on various sides. Can we go to higher particle states? Can we go to beyond large M? Can we compute QSC in different sectors to check everything? Can we compute explicitly at weak and strong coupling? Compute Hamiltonians at loops at weak and strong coupling to actually check what actually happens to the eigenstates themselves? And finally, can we take this map seriously and then use it for some kind of bootstrap? So with all of this, I thank you very much for your attention. So yeah, I'll stop here. Thank you.
Yeah, let's thank the speaker. Okay, questions?
So you mentioned connection to this matrix. What you have in mind precisely?
Okay, so
Flat spaces
think-
matrix. Yeah. Why?
right. So the idea would be basically so there is some technology which can be used to compute. So using this S matrix bootstrap, you can compute flat spaces matrices in the flat space limit of ADS basically, and essentially what one can do in principle is one can take this this setup that people have there and input really strong coupling dimensions of states of states from n equals 4, and try to see if one can actually so you take really strong coupling and really high states states high up in the spectrum. So that ensures two things. That ensures one that that you're in the flat space limit, and two that you can approximate your OP coefficients essentially by the free ones. And then once you can do that, you can combine these two things together into some formulas that give you the flat spaces matrix if you know the CFT data in order to extract them. So that's kind of the very rough idea. I can't give you too much more detail because this is also something that we're looking at very recently. So I don't understand it that well, but that's the rough picture.
Okay, thank you.
Okay. Questions 1. Questions 2. Okay, if there are no questions, then let's thank the speaker again.
Thank you.
Okay, and let's call it a day.
Thank you.
Thanks.
Okay. Thanks a lot. Thank you.